Okay. Okay, Chemistry 3101. Here we go. Chapter 8, Addition, Reactions, and Alkenes. So what you're going to see is that the focus of this chapter, the substrates that we're going to be looking at virtually in every reaction will be an alkene. If you remember in chapter 7, the substrates were always an alkyl halide or a tosylate or maybe a mesylate or a triflate. But again, here in chapter 8, we're only going to look at alkenes as being our substrates. Now, if you're wondering, what is an addition reaction? Well, the reason they have to use plurals is because there are many types of addition reactions. Now, we looked at elimination reactions in quite a bit of detail. In chapter 7, we talked about E1 and E2 reactions, and we said, okay, well, we can start with an alkyl halide or a tosylate, and we can do an elimination in E1 or an E2 to make an alkene. So here, what we see is that addition is the opposite of elimination. We're going to start with an alkene this time, and we're going to add something to the molecule. So what happens during an addition reaction is that the carbon-carbon pi bond is going to be converted to two new sigma bonds. And we're going to make two new sigma bonds. They could be to two groups that are the same. X and Y could be the same, or they could be different. Now, this table here, table 8.1, just gives us a little introduction to the types of addition reactions we're going to look at. We'll look at them quickly here. The first one is called a hydrohalogenation. And a hydrohalogenation involves the addition of a hydrogen and a halogen, as you can imagine. And the halogen X can be either chlorine, bromine, or iodine. We're never going to look at HF addition, and there's a good reason for that, and we'll talk about that briefly. The next one is a hydration reaction. And you can imagine, well, hydration must, if I'm dehydrated and I hydrate myself, I'm adding water, right? So what's water made out of? It's made out of a hydrogen and a hydroxyl. So that's what we're going to see is the addition of a hydrogen and a hydroxyl. The next one is a hydrogenation. This is going to involve the addition of a hydrogen molecule, so H2, which again, you draw the Lewis structure. So we're going to add one hydrogen atom and another hydrogen atom. It's kind of a cool reaction because hydrogen is highly flammable and explosive. So we're going to talk about that a little bit. The next one is a halogenation. So that means we literally just add a halogen, and you know that halogens are diatomic molecules. So we're going to add either Cl2 or Br2, either one of those. So we could either have two chlorines or two bromines. The next one is a word that students tend to forget, but I'll remind you of that. It's halohydrin formation. It's where you add a halogen, either chlorine, bromine, or iodine, and a hydroxyl. Okay, so it's kind of like you have an alkyl halide and an alcohol in the same molecule. So it's kind of interesting. And the last one is dihydroxylation. So you're adding two hydroxyl groups, 2 hydroxyl groups. And if you notice, dihydroxylation is actually covered in two whole sections. And there's a good reason why we have two sections based off of one type of addition reaction. And again, we'll talk about that, of course, in a lot of detail. So there you go. Those are all the different types of addition reactions we're going to look at. Of course, this is not an exhaustive list. You know, organic chemistry has been studied for a long time now, over a century, and so chemists have come up with all kinds of addition reactions. But these are key reactions that all organic chemists need to learn. All right, so let's start by talking about the pi bond. And right, a pi bond. Well, how can a pi bond get involved in an addition reaction? Well, we can think about the electrons in a pi bond as behaving either as a base, right? Because what's a Lewis base? It's an electron donor, right? A Lewis acid is an electron acceptor. A Lewis base, again, is an electron donor. So we can think about the pair of electrons in the pi bond as being a base, or you can think about them as behaving as a nucleophile. And if you're wondering, you know, how could they be a nucleophile? Well, if they're in the presence of a strong enough electrophile, they'll behave as a nucleophile. You've got to have something that's a really strong electrophile. And oh yeah, the pi bond will behave as a nucleophile. Okay, so again, the pi bond is an electron pair donor that can behave as a base or a nucleophile depending on the situation. Well, what about alkenes in nature? You know, we're learning about where we learned how to name alkenes, and we're going to look at how to use alkenes as substrates for all kinds of different reactions. You might be wondering, you know, where would I find an alkene in everyday life? Well, I'm here to tell you that there's maybe not Avogadro's number of compounds, but there are thousands and thousands of cool organic compounds that possess double bonds that have alkenes in them. For example, limonene, if you like the smell of lemons and oranges, and they do have very fragrant odors that are very strong. You know, if you think about it, the odor of oranges is very strong. So limonene, you can see, is just this little natural product or this natural compound, and it's got two double bonds in it. So it's got two alkene functional groups in it. And another one that you might not have thought of before is cholesterol. It ends in -ol. It's actually an alcohol in terms of its, the highest priority functional group. But if you take a look at cholesterol, it's got an alkene in it. Right, and cholesterol is, found in cell membranes, and it's used as a precursor for, the synthesis of hormones, and it's found as, a precursor for the synthesis of cholate and chenodeoxycholate, which are found in bile. So anyhow, we could sit around and talk about that all day. But if anybody is interested in the petroleum industry, I always have one or two students who are interested in the petroleum industry. Well, simple alkenes like ethylene, and you should know the name of ethylene, or propylene. These are alkenes that are precursors for all kinds of organic compounds. Okay, if you just take a look at ethylene, ethylene's a gas at room temperature, but it can be used to make ethanol, ethylene glycol, which is antifreeze. It can be used to make vinyl chloride, which can then be used to make things like PVC, which is found in PVC pipes, polyvinyl chloride. Can be used to make acetic acid, polyethylene, which is another polymer. Propylene can be used to make polypropylene polymer, which can be used in things like polypropylene ropes, for example. Cumene is another aromatic compound that I don't know why we don't get you to memorize the name of it, because it's so common, cumene. What else? Acetone, propylene glycol, which can also be found in different types of antifreeze. Anyhow, so again, alkenes make great precursors. You can see that, you can make all kinds of things from even the simplest alkenes. So very cool things you can do with alkenes. Well, I'm going to leave section 8.2 there, and I want to get into the whole concept of addition versus elimination. Because if we think about addition, okay, let's say we have HX, could be HCl, could be HBr, whatever. Let's say we're adding HX to a double bond, and again, we do that addition reaction. Remember, addition is where we add something to the alkene. Remember, I told you on the first or second slide, I said, well, you break the carbon-carbon pi bond and you form two new sigma bonds that I have highlighted in yellow. Well, if we eliminate those two groups that we added, right, in an elimination, and we looked at plenty of E2 eliminations, which side is favored here? Because addition and elimination are equilibrating reactions or processes. The side that's favored, whether it's the alkene side or the addition product side, is going to depend on temperature. Now, why would that be? Well, if we look at the delta G, okay, the Gibbs free energy with respect to the addition reaction, right, which is going to be the focus of this chapter, right? That's the title of the chapter. It's addition reactions of alkenes. Well, you know that delta G, Gibbs free energy, depends on two things, right? Delta H plus negative T delta S, and I usually don't think about it this way, but this is the way the book chooses to do it. Of course, you could write it as delta H minus T delta S. But either way, what are they getting at here? Well, we know that delta H is going to depend on mostly on bonds, right? The enthalpy term is mostly going to depend on bonds. And we're breaking a pi bond and we're forming two new sigma bonds. Now, this is going to end up being an exothermic reaction, right? Because we know, again, that sigma bonds are stronger than pi bonds. So if the delta H is a negative value, right, this is an exothermic reaction, and we want delta G to be negative, again, this is for addition reaction. This is what I'm talking about right now. Well, if my T is always positive and my delta S, could anybody tell me, is my delta S increasing or decreasing here? Why I can't see. Is my delta S increasing or decreasing? Would delta S be positive or negative for my addition reaction? I'm going from two molecules to one molecule. Yeah, absolutely. It's decreasing, right? So I have a negative. Maybe I should write that a little bit bigger, but I have a negative times a positive times a negative, right? So overall, that's going to end up being what? It's going to end up being a positive term overall, right? So if I have a negative plus a positive, as long as the temperature is low, the addition reaction is going to predominate. But if I crank up the temperature, so at low temperature, addition is going to predominate, but at high temperature, elimination will predominate, right? And again, this is just, me kind of rehashing what I just stated. Well, right, we're talking about addition reactions. So again, an addition reaction is favored in terms of delta H, enthalpy, the change in delta H. Since I'm breaking a pi bond, which is weak, and I have to break a sigma bond, okay, in this case, overall, you can see that more energy is being released than is being put in. And so the delta H for the reaction is a negative value. Now, again, we have delta G, which is equal to delta H minus T delta S. So far, we want to have a negative delta G in order for our addition reaction to be spontaneous, and we've got a negative delta H. Well, I told you that overall, you've got a positive term here, right? Everything here is positive, okay? And I think I have more information about that here. Yeah, so we said that delta S is decreasing. So my delta S is negative. So that is why when we have a higher temperature, the elimination is going to predominate. And when we have a low temperature, addition is going to predominate. And, that might be worth a value of 1, maybe 2 multiple choice questions on your next exam, okay, your next quiz. So again, at low temperature, when we have low temperature, our delta G is going to be negative for our addition, okay, our addition reaction. But when we have a high temperature for our delta G, let's see here, copy for our, sorry, I meant for our addition reaction, okay. Come on. In this case, when we're doing addition, if we have a high temperature, the delta G would be positive. Okay, so the reverse reaction would be spontaneous. Okay, there we go. All right. So let's see here. So what does that mean? Okay, if we're using lower temperatures to favor addition reactions. Well, let's start by taking a look at that first addition reaction from table 8.1, hydrohalogenation. The addition of HX to an alkene, right? So hydro, makes you think of a hydrogen, okay? So let me just, hydro means a hydrogen, and halogenation is going to be either chlorine, bromine, or iodine. We don't do hydrohalogenation with HF, okay? And I'll explain why later. Anyhow, let's say we have this alkene here. So this would be what? Cis-3-pentene. So we have cis-3-pentene. You take that molecule, okay, just regular old cis-3-pentene. You buy it from a chemical supplier, and you add hydrobromic acid to it at minus 30 degrees Celsius. Well, what you get is addition of the hydrogen and the halogen to the double bond, right? You have the halogen added to one of the carbons. And to the other carbon, you have the hydrogen. It's not shown because this is a bond line structure, but you know that this hydrogen is here, right? And there are 2 other hydrogens which are not shown as well, okay? But by now we know enough about bond line structure. So you end up adding your HBr across the double bond at low temperature because addition reactions are favored at low temperature. Well, what happens if the alkene isn't symmetrical? Right, this is a perfectly symmetrical alkene. You can see the plane of symmetry down the molecule here. So this is symmetrical. Okay. Well, what happens if you have something that's not symmetrical? Right. If you look at this alkene, there is no plane of symmetry down the molecule like this. If you take a look at these 2 carbons, I'll write one of them in red and one of them in blue. You see they're different. Right, the one in red has a methyl group and a hydrogen attached to it, whereas the other one has 2 methyl groups. So it's not symmetrical. And so if you go to add HX to that, whether it's HBr, HCl, or HI, where does the halogen go? Now, which carbon does it go to? Well, that's a question that we need to answer. Okay, that's a very important question that we need to answer because we could end up with a mixture of regioisomers. Right, you could end up with one regioisomer, let's say, where you have where you have the halogen here, okay? Or you could end up with the other regioisomer where the halogen is here, okay? Now, which one is it? Well, we're going to answer that question. Hydrohalogenation is regioselective for what we call Markovnikov addition. And Markovnikov is a last name that you're going to hear come up a whole bunch in Organic Chemistry 1. It says in 1869, a Russian chemist named Markovnikov observed that the hydrogen atoms tend to add to the carbon that's already bearing more hydrogens, right? If I go back to that same alkene that we saw on the previous slide, I forget which color I used for which one now. So the one on the left, I used red pen for, and the one on the right, I used blue pen. Well, you see that the one in red has one hydrogen, whereas the one in blue has no hydrogens to it. So what the Markovnikov rule is, or what we call Markovnikov addition, is we say that the carbon that is richer in hydrogens, which would be this one here, I'll highlight it in yellow. This is one has one hydrogen, whereas the other one, the blue one, has 0 hydrogens attached to it. So I think you'd agree that the one that is red is richer in hydrogens. So whichever one is richer in hydrogens, that's the one that takes the hydrogen from your hydrogen halide. And the other carbon is going to get the halogen. And that's what we call Markovnikov addition. Again, the rich get richer. The carbon that is richer in hydrogens is going to take the hydrogen, and the other carbon is going to take the halogen. Now, if you're wondering why is that, is there a good reason for that? Absolutely there is, and we'll talk about that in a few minutes. But before we do that, I want to propose or show you something kind of cool. Is that there was a lot of research. This wasn't something that Markovnikov discovered in an afternoon. This reaction here, but did a lot of work, a lot of investigating. And I mean, we're talking about the 1870s. This is over 100 years ago that he was doing this research. And something that he found is that sometimes he would do the reaction with HBr and the alkene, and what he would find is that the carbon that was richer in hydrogens was the one that ended up with the halogen. So this is what we call anti-Markovnikov addition. And initially he couldn't explain it, and there's a long story behind it. But basically he found out that whenever anti-Markovnikov addition occurred, he had some kind of impurity in his solvent, and the impurity in it was a peroxide, right? So this is a peroxide. It's an organic peroxide, okay? I know that this is hydrogen peroxide, but when we have ROR, that's an organic peroxide. So he had some kind of organic peroxide in there, and so he proposed, well, it must be a different mechanism, different reaction. And it's true, it is a different reaction. And in fact, we will look at the mechanism of this. We'll look at the mechanism of anti-Markovnikov addition in Chapter 10. We'll look at it in a lot of detail. And the reason it's covered in Chapter 10 is because if you've looked at the title of Chapter 10 in our syllabus, it deals with radicals. So this is a radical mechanism. Anyhow, going back to the two types of addition, we see that the take-home message is that if you start out with an asymmetrical alkene, okay, you have this carbon that's got 2 hydrogens, you have the other one in red that's got no hydrogens attached to it, we can get Markovnikov addition. This is the one where the rich get richer, okay? We have that one, or we have anti-Markovnikov, which is the opposite. And that we can control the regioselectivity based off of the reagents that we use. If we just use pure HBr, well, we get Markovnikov addition. If we throw in an organic peroxide, we get anti-Markovnikov addition. And what can you do with a tertiary alkyl halide? Well, I could do an elimination reaction. I could do an E1 reaction. I could do an SN1 reaction. What could you do with a primary alkyl halide? Oh, wow, I could do an SN1, or sorry, an SN2 or an E2 reaction, right? And I could control the type of product I want. So with that information in mind, basically what's covered right here, okay, we've covered 2 reactions so far. We've covered Markovnikov addition of HBr, and we've covered anti-Markovnikov addition of HBr, which requires an organic peroxide. All right, let's try a problem. This is conceptual checkpoint 8.1. It simply asks us to draw the expected product, major product of the following reactions. Okay, so we're taking 1-methylcyclopentene and we're treating it with HBr. So again, these are just addition reactions. So would this be Markovnikov addition or anti-Markovnikov addition? Can anybody tell me? Based on what I told you. Yeah, exactly, Jonathan. It's Markovnikov addition, right? Because we're just adding HBr. In fact, all of these, yes, you're both 100% correct. All of these are just Markovnikov addition. So that's what this whole question is about. So Markovnikov addition. If we look at the double bond, right? We have this carbon, I'll write it in red, and then we have the carbon in blue. Could anybody tell me which one of these carbons is richer in hydrogens? Yes, it's the one in blue, because the one in blue has 1 hydrogen, the one in red has 0 hydrogens. So that means in our final product, we have our 5-membered ring. Okay, we have our methyl group. This carbon, the one that was richer in hydrogens, that now has a 2nd hydrogen, and the carbon that's in red is the one that's going to take the bromine, like that. Okay, so that's going to be our final product. If we take a look at the next one, I'll put this one in blue and this carbon in green. Which one of these carbons is richer in hydrogens? The one in blue or the one in green? Yeah, absolutely. It's the one in green. It's got 1 hydrogen attached to it. So again, if we draw out our molecule, our final product, this carbon is the one that's going to take the hydrogen. This is a bond line structure, so I'm not going to draw it in. And then we're going to have the bromine attached here. And then the last one, I think you're getting the hang of it by now. We have this one and this one. Well, the one that's in red has 1 hydrogen attached to it. Therefore, our final product will be this. We have a methyl group and a chlorine, like that. And there you go, just some Markovnikov addition reactions. I can't stress to you enough how important Markovnikov addition is. When I was in graduate school, I went to go watch a defense of a guy who had just completed his PhD, and even in a PhD defense, they asked him a question about Markovnikov addition. So that's how important it is. Another funny thing about this question is that you probably noticed that all of the compounds are achiral. Notice that every product is achiral. All products achiral. So we don't have chirality to worry about. And if you're wondering, what would happen if I have a chiral center? Well, I guess we're going to have to address that later since it wasn't covered in this one. And in order for us to address that, we need to take a look at the mechanism. Okay, so let's take a look at the mechanism of Markovnikov addition. Good news, it's not long. It's a 2-step process. It's a proton transfer followed by a nucleophilic attack. So in the first step, your pi bond, the pair of electrons, kind of behaves as a base, and it accepts a proton from the HBr, and you form a carbocation. Okay, now that you've got a carbocation in a bromide ion, the bromide can come in and attack just like that. Okay, now in terms of the mechanism, it says the step with the highest activation energy is the rate determining step, which in this case, in the hydrohalogenation reaction, is the proton transfer. Okay, it's got the highest activation energy. You can see that it's by far bigger, right? This one is much smaller. Anyhow, so that's going to be our rate determining step, is going to be the proton transfer, which leads to the carbocation intermediate. Now, in terms of, why do we only get one product? Why do we get the Markovnikov addition, right? If you examine this alkene, you see that this carbon has the hydrogen, and so it's the one that takes the hydrogen, and the other one forms a carbocation, like that. Okay, well, if we go back here, okay, if we just take a look at the first step in the first reaction, okay, like this. If I draw that starting alkene like this, okay, and if I write out HA like this in my reaction arrow, look, if the carbon that's richer in hydrogens takes the hydrogen, what do I end up with for a carbocation? I don't have a lot of space, but I'll do my best to write it out here. You end up with this carbocation. That's a tertiary carbocation. Okay. If it was, I'm going to write this in blue. This is incorrect. But if it was to add at the blue, at the other carbon, so let's say, well, that looks like crap. Okay, let's say it did this. And it doesn't do this, but if the rich didn't get richer, okay, if the hydrogen get added to this carbon like this, maybe I can write the mechanism a little better, like this, then what would you end up with? You'd end up with this. Let's write it down. You'd end up with a secondary carbocation. So this is the answer. Okay, this is the man behind the curtain, right? This is the reason why the rich get richer, because you end up with the most stable carbocation. If the one that's poorer in hydrogens takes the hydrogen, you end up with a less stable carbocation. And so that is the answer right there. That is why Markovnikov addition always occurs, because you proceed through the most stable carbocation intermediate. This is just showing it with that same alkene that we just took a look at. Again, if you added it to the carbon that is poor in hydrogens, look, you end up with a secondary carbocation in this case. Whereas if you do the Markovnikov pathway, which is, again, going to give us their final product, you see that the rich get richer and we end up with a more stable carbocation. Okay? So Markovnikov products are formed because of carbocation stability. That's the answer right there. Now, so that deals with regioselectivity. But what about the stereochemistry? What about the stereoselectivity? Well, you can imagine that if I have a carbocation, we know what the molecular geometry of a carbocation is, don't we? Right? If we have one butene and we draw the first step of the reaction mechanism, right? The rich are going to get richer, okay? You could do it like this if you want, but I always like to drag the arrow through the carbon that's going to take the proton. You're going to end up with this carbocation, okay? Like that. Well, you know that this carbon is sp2 hybridized, and it's trigonal planar. That means that the nucleophile, the chloride, can come in, right? The chloride could come in and it could attack from the back or it can attack from the front. Doesn't matter. So that means you're going to end up with a racemic mixture, right? You end up with both enantiomers in this case, both R and S, and they're formed in equal amounts. Give me a thumbs up if that makes some sense to you. Give me a thumbs up if two things make sense. The Markovnikov concept of its addition and the stereochemical consideration, rather. Does that make sense to everybody? If not, I can go back over it a little bit. Okay, good. And what you're covering, remember, this isn't simple. Okay, if it was simple, everybody on the street would be able to do it. You could walk up to anybody, you walk into Walmart, you're shopping, you talk to anybody there, like, hey, do you know about Markovnikov? Yes, I know it. No, probably most people don't. Okay, it's not simple. So again, if you have a question, don't be shy to ask. But again, just to repeat myself, and the reason I'm repeating myself so much is because I'm 44, I've earned the right to do it, like an old person. But it's so important that you understand why, number one, the regioselectivity. So that's what's being explained on this slide. You go through the most stable carbocation. And then in terms of stereochemistry, you understand that a carbocation is going to be trigonal planar. The nucleophile can come in and attack from either face of the molecule. If you understand that, my friend, you are you understand it really well, okay? Because the next slide is just rehashing what I just told you, that a carbocation is sp2 hybridized, okay? It's trigonal planar, all right? So the nucleophile can come in and attack from either face of the molecule, so nothing new there. But I know that all of you are very astute students, okay? And you're always looking out for, hey, what else could happen here? And I bet you that there's somebody here who's already thinking, well, if the intermediate is a carbocation, I remember way back in chapter 6, one of the key mechanisms that I learned was carbocation rearrangement. So, hey, if I do a Markovnikov addition and I end up with some kind of goofy carbocation, pardon my language, that could rearrange, will it happen, Mr. Dion? You can guess that the answer is yes. Okay, so let's take a look at this right here. There's nothing wrong with that alkene. That's a perfectly legit alkene. You see that the carbon that I'm highlighting in red has two hydrogens. The one that I'm highlighting in blue only has one. The rich get richer. So you end up with this secondary carbocation, but look like it can happen. A hydride shift can happen, and we go from a secondary carbocation to a tertiary carbocation. Notice that this is in equilibrium, right? The proton transfer, but notice that the rearrangement is not in equilibrium. Remember, if there's something I want you to remember here, it's that if carbocation rearrangements can occur, they do. Okay, they do. They just do. So here we get a hydride shift, and so not only do we get Markovnikov addition, sure, that's cool. Like the proton transfer is totally Markovnikov, but we get that rearrangement, which gives us something that we kind of got to be on our toes, to realize like what the heck happened here. Well, the reason that we ended up with this tertiary alkyl chloride is because there was a carbocation rearrangement. There was a hydride shift here. Okay, remember, when carbocation rearrangements can occur, they do occur. And I have that written on the next slide right here. So usually what happens is that you can never get lucky enough to just get the rearrangement product. You would normally get a mixture. Okay, you would normally get a mixture. I don't know if any of you have taken maybe an introduction to organic chemistry class before. Sometimes I have students that have done that. But if you've ever run a TLC before, and there might be some of you who have, whenever you run a TLC, which is a thin layer chromatography, and you might learn that with Mr. Geiger in the lab, I don't know, but you usually see mixtures of products in organic chemistry. It's pretty rare to just get one product. So there you go. All right, well, with all that in mind, I have a question to ask you. I don't think it's a simple question, but I think it's a doable question. The first one here, we'll call it 8.2a. I don't know if it's A or B or what, but in 8.2a, if you take a look at the alkene we're starting out with, this carbon in blue has no hydrogens, but this carbon in red has 2 hydrogens. Based off of that, could anybody tell me, would this be, or what would my reagent be? I'll just ask you that. Could anybody tell me? It's easy to answer in the chat if you want, or if you want to unmute your mic, you can do that too. What would my reagent be here? Yep, Bruna, you're 100% correct. Mackenzie, yes, absolutely. It's just HBr. Yep, that's it. HBr, nothing else. This is just a Markovnikov addition. Markovnikov addition. Could anybody tell me what's different, what the next one, what you would use as your reagent in the next one? And again, it's not a trick. Not trying to mess you up. We're just kind of practicing what we've looked at. Could anybody suggest a reagent for here? You might have to go back in your notes and look for a second. Well, is this a Markovnikov or an anti-Markovnikov addition? Right, this is an anti-Markovnikov addition. Anti-Markovnikov addition. Yes, absolutely. It's anti-Markovnikov. So we need HBr and what? We need an organic peroxide. Okay, ROOR. If you're wondering what ROOR is, there's all kinds of inorganic peroxides that can be used, like benzoyl peroxide, which looks like this. Okay, and we'll talk more about that later on, but this is an example of a peroxide that you could use. Okay, all right. So let's take a look at a question, a practice problem. This is still section 8.4, hydrohalogenation. Just says predict the products for each of the following reactions. In some cases, you may get a carbonality center, maybe not. So let's see. You know what's great about these questions, or what I think the best way to tackle these kinds of questions are? Let's call this one, we'll call this one A, we'll call this one B, and we'll call this one C. I think the best thing to do with these is to draw out the carbocation intermediate, because that really helps you kind of understand, what your final product might look like. So if we just draw the first step, the rich are going to get richer. That means this carbon is going to take the proton. So I'm going to end up with a tertiary carbocation. I'll draw it. It's going to look like this, where we have the positive charge here. Okay, remember the proton was added right here. I'll delete that. So now bromide can come in and act as a nucleophile. Okay, my bromide can come in and act as a nucleophile. Maybe I need to think about how I draw that curved arrow. Maybe I'll draw it like this. There we go. So can anybody tell me, would I end up with a new chiral center here, yes or no? Like, yes, chiral center, no chiral center. In my product, would there be a chiral center? Yes, no? Yeah, absolutely. Yes. I totally end up with a chiral center, don't I? And so you'd actually end up with a mixture in this case. Oops, I wanted to use my black pen. Here it is. So you'd end up with this, where you'd have the bromine in the back and the methyl group coming out in front. And then you'd also end up with the enantiomer, right? Where you'd have the methyl group in back and the bromine coming out in front like that. There you go. So you'd end up with both of those. All right. There we go. I'm kind of running out of space here, so let me just move this a little bit. So I'll end up with this plus this. All right. Okie doke. Okay, let's try the next one. We have HCl. HCl. So the first step is going to be proton transfer. The rich are going to get richer. So let's draw the carbocation. It's going to look like this. And this. So in this case, I'm not going to end up with a new chiral center, will I? When the chloride comes in and attacks, I'm going to end up with a plane of symmetry in the molecule, right? You have a propyl group here and a propyl group here. And so after the nucleophilic attack, you only end up with one compound. You just end up with this guy. There we go. So no chiral center there. And then in the last one, again, practicing. This is really good practice. Oops, not HBr, it's HI this time. Come on. Go. So the rich are going to get richer. If you're still wondering, why, how are you doing this? Well, look, this carbon has a hydrogen, and this carbon over here in blue has no hydrogen. So when I draw the curved arrow, I'm going to draw it from the pi bond, drag it through the carbon that's going to take the hydrogen, like that. Okay? I find that just handy. So then when I draw the carbocation, I know that this carbon has the two hydrogens. This methyl group here, and I have a positive charge there, and then I have the CHEM dimethyl like that. I just leave these hydrogens out because this is a bond line structure, so I just get rid of them like that. And then my iodide is going to be my nucleophile. It's going to come in, so I'll draw iodide. You can draw in all the lone pairs like that. Okay. The iodide is going to act as a nucleophile. Okay, let me fix my curved arrow. Maybe I'll draw it like this. There you go. And am I forming a new chiral center? Could anybody answer this? Would yes chiral center or no chiral center? The product. Would you get a chiral center here? Yes. Awesome. Awesome. You know what that tells me? It tells me that my students really understood chapter 5, right? The chapter on stereochemistry. So we're going to end up with a stereoisomer. Put the methyl group up like this. And the iodide down here. And you can write, if you just want to write plus enantiomer, that's totally fine. There's nothing wrong with that at all. Maybe you want to write out the other enantiomer because you just love writing out structures. There's nothing wrong with that. So the iodide there and the methyl group down here. Either way is perfectly fine. So you saw that in two of the cases, we ended up with a pair of enantiomers, and in one of them, there's a plane of symmetry in the molecule. And so, yeah, there was only one compound formed. Let's try another one. We're still on the topic of hydrohalogenation. I don't want to leave it yet. I want to try one more question. I'm going to go just grab a quick drink of water. We're not taking a break. I want you to try to draw a mechanism for this on your own, and I'm going to come right back. So just give me a second. I'm just going to grab some water. All right. Oops. Learn students. Sorry, my MacBook timed out here. Just give me a sec. Oops. Come on. My computer's really trying my patience here. Okay, there we go. So I have a question. It's tough for me to ask the question, but could anybody tell me what would be the key step in this mechanism? Could anybody tell me, not the rate determining step, but there's a key step in here that, if you're trying to explain what's happening in this reaction to a friend, could anybody tell me what the key step would be here? Or the key mechanism or key portion of the mechanism? There's something interesting happening in here. Yes, Edwin, 100% correct. Yes, there's a rearrangement, isn't there? Right, and Edwin says a hydride shift. He's 100% correct. Yes, absolutely. So that would be what I would consider the key step. I think that's what makes the question interesting. Let's take a look. We're doing a Markov-Nikov addition, so the rich are going to get richer. This carbon's going to take the proton. Let's draw what the carbocation looks like. So it's going to look like this. It's a secondary carbocation, but as Edwin says, there's a hydrogen here, and so we're going to get a 1,2 hydride shift. So this was a proton transfer. Now we're doing our carbocation rearrangement, and now we're going to end up with a tertiary carbocation, aren't we? Beautiful. Just like that. And then in order to make the tertiary alkyl halide, the bromide is going to come in and do a nucleophilic attack like this, and there you go. Okay? Perfect. Excellent. Excellent work.